Hello, my friends. This is Dr. Mohamed Nezami again with another presentation on RF and microwave devices. We have done tens of these videos on passive components, and you can check my playlist and the list of videos and join my channel. But today we're gonna diverge into something a little bit different. Today I'm gonna go through an example of an antenna, microstrip antenna, which is a lot of people have designed small flat antennas for SATCOM applications. But today, in particular, I'm going to cover a design of a GPS global positioning satellite antenna, which is a little bit unique, that it has dual stacked elements, and the signal is picked up and offered, circular polarized signal is picked up, and we have two dual feeds for both batches. So the antenna simply has four feed probes to the elements, which means that you're picking up the horizontal and vertical separately from the circular polarized signal. And the reason we do this, I'll show you in a minute. It has to do with being able to actually pick up both signals, in the circular polarization wavefront, so that you can develop the power and line them up so that the vertically and horizontally actually are in phase. Just before we go on, just a little advertisement. I have a coming up next month is a 3-day hands-on training on RF and microwave device designing using 3D modeling. In this case, I'm going to be using HFSS for this training. We will be covering a whole bunch of stuff from amplifier, they're all passive this time. We're going to cover filters, hybrid splitters, couplers, antennas, combiners, radial combiners, OTMs, and several other devices. And this training will be a hands-on training, so it'll be held here in Jerash, Jordan. And the fee for the course is pointed out here. And then this fee actually includes the accommodation for hotel stay and the breakfast and lunch as well. So, okay, so let's go on. So today we're going to cover a presentation on dual band, dual polarized global positioning system antenna. Okay, and this antenna really is going to be an antenna that would be used for GPS receivers, and primarily not so tiny receivers like the ones you see in your watches and in your cell phones. This is more like platforms that are a little bit larger, industrial surveying, asset control, and so forth. Okay, just to build up some background, the global positioning satellite system around the world, if you go out and look at the sky, there are more. Actually, there are 5, but let's just say there are 4 for right now. Systems that are out there orbiting the Earth and sending signals, from which receivers on the ground receive only terminals on the ground. GPS receivers receive these signals, and they can determine your location and time and give you a reference clock of some sort. And these systems, if you look at the frequency allocation of these systems, they're basically owned by major countries in the world, economical countries, like Baidu system is Chinese. The GPS system, which is extremely widely used, is US, and of course, it was the first to be there. The Galileo is a European system. And then we have the Russian system, which is GLONASS. And I believe there is an Indian system, which I can't recall the name of it right now, but there is one for India. And all of these transmits beacons in the signals in the L band. The L band is basically somewhere around, I would say, historically, L band is probably from 1 to 2 gigahertz. But L band here is like from 1.1 all the way to 1.6 gigahertz, okay? Primarily, a lot of times we're focused on, there are two, and it's beyond the scope to go into the signaling, but there are two systems that we're going to look at. Basically, is the L1 designation, which is centered at 1575.42 megahertz, and the L1 system, which is centered at 1.22760 gigahertz, okay? So these two systems are basically the two systems that are primarily used in a lot of commercial applications and for surveying as well, okay? So if we're building a front-end antenna and a front-end for GPS receivers, you know, most of these industrial systems that you see, you will see an antenna assembly within a LNA that get attached to a vehicle, and then a cable goes down beneath to the modem. And the modem, well, or the receiver, in this case, there is really no transmission in this, but the receiver actually is the one that processes, takes an IF signal, or even this signal, amplified and filtered, and digitizes it, and it actually goes in, and there's digital signal processing algorithms that extract coherently your location based on at least 3 of those satellites. So the antenna that we're going to be designing has to have at least, it would have to see at least 4 satellites, which is like 140 degrees span or beam width, we might say. So this is called the lower L band, and this is called the upper L band, or what we're going to say from now on, we're going to designate these by L1 and L2. All right, so if we look at the, if we're designing an antenna, we have to, of course, see the bandwidth of the signal that we're receiving, okay? So this slides here, it shows the various satellite GPS systems with the sort of like a cartoon showing the bandwidth of the modulations, okay, of the signal bandwidth. And let's just focus that we're interested right now to look at is this one here, which is the L2 band, and the L1 band, which is right here, okay? And the L1 band is centered at 15.75, and you can see that for this signal here, we're going to need at least 2 megahertz wide signals, okay, because that's what the chipping rate on this one here. So the bandwidth is roughly that, okay, or actually it's plus minus twice that, which is 2 megahertz. Oops. Okay, so the L1 is basically plus minus 1.023 megahertz, okay? But most of the systems that we have nowadays, they have at least 20 megahertz or 10 megahertz of bandwidth. So, and that's what we're going to go with, is somewhere around there. Okay, so let's just look at the simplest GPS front-end low noise amplifier. Okay, this is an assembly that basically picks up the signal with an antenna, that low profile antenna, microstrip antenna, and then amplifies the signal. It would get a signal that is below minus 120 dBm, and you have to give it down, amplify it with a low noise figure, and try to preserve the bandwidth and reject interferences, and then pass it on to the receiver with an amplitude of, say, at least minus 70 dBm, okay? Somewhere between minus 50 to minus 70 dBm, okay? And then that one too has to amplify it all the way to get to the 80 dB appropriate level, which is somewhere, sometimes it's like 10 dB backed off from full scale, and full scale is 0 dBm. So you're talking about 50 dB in the front end amplification, and then an additional probably of 40 dB amplification in the receiver, okay? Of course, the antenna hardly has any gain. These antennas that we're going to talk about, usually they have tiny gain, 1.5 dB or 2.5 dB at most. We're talking about antennas that are simple antennas. There are some array GPS antennas, which of course they gather more signal and they beef up the RF level. But let's just look at this. So we have an antenna that basically picks up. The antenna is something like this. Because there are two bands, you've got L1 and L2. L1 is in the 1.2 gigahertz, which is the lower one. That's the larger one. As you know, it's a larger wavelength, lower frequency. And this one is the, this is the L1 up on top, and this is the L2. The L2 is the one which is 1.227, okay? L1 is 1.575, some fractions. So the L1 is on top, and the L2 is in the bottom, okay? And then you get a signal that is fed to the receiver. And in this case, of course, the signal that these picks up, it's circularly polarized. Satellite sends the signal circularly polarized so that it can mitigate its, the atmospheric and the ionospheric and the multipath and fading issues. But the antenna itself is designed so that it can pick up the L1 band and the L2 band, okay, on separate polarization. And that's what I indicate with these arrows in here. For instance, this is the horizontal L1, L2, and this is the vertical L1 and 2, okay, extracted from the circularly polarized signal. So since they're 90 degrees apart, as you can tell, the vector pointing of the signal being received, we use a quadrature splitter to actually align them in phase. And that's what I indicated here, where this one here, we shift it 90 degrees, okay, and it becomes in phase with this one. Because this signal here propagates 90 degrees, this one is 90 and another 90, okay, so therefore it's 90 degrees off from rotated, and it comes in phase. And these hybrids, you've seen them probably, they're like this, some of them ceramic, some of them are microstrip basically. And then you go into filtering, of course. The reason you want to go into filtering indicated in here is that the 1.575 and the 1.227 gigahertz corresponding to L2 and L1, there is some interferences that comes in. So preferably you want to go ahead and try to filter. And when you try to filter, of course, you want to use a single filter. You're not really you're trying to make this as cheap as possible. So use a common filter for both paths, and you end up with picking up some of the distortion, the interferences in there. So you amplify, and then you filter again, then you amplify to build up gain. And what you end up with is this here, this scenario. And this scenario, if it goes in and gets digitized, of course, this interference in here causes some compressions and some issues. And you can see that the nonlinearities of these amplifiers in here caused some of the interaction between these interferences to fall in band right on top of the GPS signal. Okay, so this is an issue. So in a lot of cases, a lot of people say, well, I don't want to use this. Let's go another way to mitigate this issue here. And that is basically to split off the bands separately. So since we're using two separate antennas, each one, let's make each one have two feed probes that are orthogonal. And then we combine them again and amplify and then combine them later on when you filter them and they're very clean. And of course, you can combine them and process them in the same A to D because they're so close in frequency and the levels are controlled. So here's an antenna, which is in this case a stacked antenna. These are commercially available. There's like tons of companies that build these ceramic antennas, and you buy them from China for fractions of a dollar, so they're pretty cheap. So you get the antennas, and there are two antennas here, L1 and L2 designated, and each one of them will actually have two feeds. And the two feeds, they're vertical and horizontal. They get lined up with the quadrature hybrid, the 90-degree hybrid, okay, which what it does, it phase shift 90-degree one of the elements so that they are actually in phase. And then, of course, they all contain the interferences, okay? But what happened in this case, we have for instance, this path here is the L2 path, which is the lower frequency one. As you can see, what we can do is we can filter out, get a narrow filter that we can filter out only the L2, and the interference all gets rejected. And if there's any leak, if the antenna, the L2 antenna, if it picks up L1 signals, those will be rejected as well. So you get a very clean signal, you amplify, and then what you end up with is a nice, strong signal with minimum interference on L2, which is 1.227 gigahertz, where likewise, you can see that the other signal, which is 1.577, which is the L1 band, okay, we filter that as well, and then we amplify it again, and you end up with a signal. Of course, these filters are ceramic filters. They are very, very sharp filters, and I just happen to pick up small ones, but sometimes these are much larger than this one here, okay? So, and then we add them up, and what you end okay, so when we pick them up, we end up with the dual band L1 and L2 signals going into the receiver with minimal interference, okay? And this is very nice because we can now get very accurate time base and spherical coordinate for estimating your location. So again, the scheme here uses two separate feeds and two separate elements, which gives multiple degree of freedoms to cope with high RF interference. This figure is taken, by the way, from a paper that I published. You can Google my name on ResearchGate, and it's posted on there. I will try to put the link down in the more info below this video here. Okay, so let's go to the antenna. The antenna is basically, we know that before we could do this, let's look at what's out there in the market. If you type on Google GPS antennas, you end up with hundreds of these antennas made all over the world, and a lot of them are Chinese. And all of them, literally, they come in variants like this, okay? Sometimes they would be a single band, okay? Or dual band with a single element. And sometimes they would be stacked, like in this case and in this case. They're stacked. And sometimes they have a single feed. You can see here, there's a single feed, okay? Or a dual feed. This screw here, that's a screw just to hold this batch here with this batch to the board, okay? Because this batch here, the L2 here, this is the rounded batch, and the L1 in here, and a lot of times they have glue. You attach them, you attach this one to this one with a glue, and then you have dual feeds that go in from the bottom of the board through the L2 element, there would be holes that will let the pins come to this surface and get soldered here. And these are both orthogonal feeds to the L1 band that is here, where the L2 band has also two of these on this side, but you don't see them because right now they're obstructed with the L1 here, but they're below here, okay? This one you can see here that it has only a single element, but it does have a dual dual orthogonal feed. Same thing in here, same thing in here. This one doesn't, okay? So today, the design I picked to demonstrate is based on, I surveyed the antennas on the literature, and I just happened to pick up one where it has two batches, and it's circular. The first one down below is the L2 one, okay? And it's basically a circular batch resonator antenna, resonance antenna at predetermined center frequency of L2, which is 1.227. And then it has 4 eye slots. We call these eye slots, okay? Well, you can see that the green here is the substrate, it's exposed. And then the top one is the L1 batch antenna, and it has a crossed slots. These slots are what we call them for meandering the surface current, out of surface current, so that we can actually reduce the size of the antenna. As you know, batch antennas, they all have to resonate at a half wavelength, okay? If it's a square, it's got to be a half wavelength, length and width, okay? So sometimes if you would want to make sure is try to reduce the size physically, and this is one of the methods to reduce it so that this here resonates at the desired L1 and L2 frequencies, but at a smaller physical size, okay? And it's beyond the scope of this video to go over that, but you can dig into the publications and see that. So why I'm building this, why is this different, is the following. The antennas that I just showed, these ones here, you may have noticed that they're all ceramics, but they're all thick. You can see that a lot of these are almost 1/2 inch or 4/10 of an inch. And the reason for that is to actually get better gain and better bandwidth, okay? Of course, doing it this way, it's heavy, and it's heavy, it can get damaged. So I thought of, let's just see if we can make this on a substrate and get almost the same performance from, say, a 64 mil with substrate, both for L1 and L2. And so that's what I did. And so before we do that, let's just go to HSS. And so this is what I have right now. So I laid out a, this is the L2 batch, and this is the L1 batch in here. And then I have the slots, of course, in here. And then what I have beneath is actually 4 feeds. And these 4 feeds, actually they're to pick up the vertical and horizontal from both bands, and they are basically distributed. Let me see if we can. Okay, you can see here. There's one. They're 90 degrees. Okay, like this one here. As you can see, this is the one on top. So it's soldered to the top. Where the one below, you can see the holes in there to get to get to the bottom, okay? I'm sorry, no, I meant the other way around. I apologize. This is, if we go, let's see, look at this way. Oh, okay. So you can see here, this is one feed, and this is another one, and you can see that these two here, the shorter ones, are for the L1, and you can see the center pin going to the top and getting attached to the top, okay? Which that's this copper, this patch here. Okay, so let's go to the upper patch. You can see the upper patch in here. This is attached to this one and this one. Now there's the other feed for the L2 is down here. You can see it, and that one is basically hooked up to the lower batch in here. Okay, so the antenna itself is made of two stacked, and the material I'm using is Arlon AD430 for this material. So before we see the performance, let's just get back and talk a little bit more about how the antenna is designed. Now, like I told you, the publication has a lot of these antennas, okay, and that antenna I picked up from one of the publications, and it did not work, honestly, the way they designed it, but I had to, a lot of these, it's unfortunate that you look at some conference, especially conferences sometimes, conference papers, is you try to repeat the results and you realize that these guys really, sometimes they didn't really report actual designs, because you can build it exactly with same dimensions, with the same material, but still did not get the performance. And in fact, in that case, it didn't even work for the substrate that they've used. So I ended up almost, it's a different design by the time you optimize it and figure out, make it work. But anyway, you see these batches of antennas laid out in the IEEE. There's so many of them. And for instance, this one here uses the centered crossed slots, and the feed is right here. So that's where that one, the difference between this and the one I've used is that I've used one circular, this is a square, but it's exactly the same math, except of course for the resonance dimension. This one is the one that's circular, and it's reported, so you can these are actually from the one of the books. I think it's called Low Profile Antenna Book. I grabbed it, but it's also a publication in the IEEE. So again, like I told you, the reason for this here is the fact that you can resonate at the same frequency, but at reduce the size of this, and that's meandering. That's what we have. Again, the same one in here. Here, you can also make it square. So these are very common. So let's go through the antenna that I have right now. So we have the top patch in here, the smaller batch. As you can see, for a higher frequency, you get a shorter wavelength. So this one on top is for L1, okay? Where the lower one, right underneath it, is for the L2, okay? And so we've got slots. The top one has the cross slots, and the lower one has the edge slots. And this is very clever because, as you can see, we can't really use the crossed eye slots and the bottom one, but we do use it here where it's exposed, because you have to use it on an exposed surface, okay? And then the feed, like I told you, so we've got, this is a sideway view. There is a copper batch up on top, which is for L1, and there's a copper batch underneath it, which is for the L2. This one is larger than this one, of course. And then the feed, you can see that the feed, there's two dual feed that feeds to the top, okay? And there's another feed that feeds to the bottom as well. And they're both orthogonal. So these are orthogonal feeds for the L2 batch, and this is for the L1 batch. Another view on this from the bottom, you can see, and this is basically a coaxial line right now, but you can, so, but in actual life, and one of the systems I've designed, where I designed an integrated LNA on top of this, you really pick up the signal. You have an additional layer, because this is the bottom of this, of course, is ground. There is a ground side on the bottom. So below the ground, there is another batch which holds the active circuitry. So really in real life, the probe comes through the layers and onto another microstrip line below, And that's where you implement all your LNA circuitry. So again, let's look at the lower batch right now. So the lower one, we've got this eye slots, okay, and then we've got the feeds that are soldered to the batch itself. These feeds orthogonal, and then we've got a hole in here. This exposed via here is really is cleared so that you can take the signal to the top batch, to the L1 batch. And what you see here is this is the center conductor, okay? So the hole, we don't want to make a hole on the, drill out the whole entire area, because we really need to use this as a medium, as a dielectric medium for the center pin to make up a coaxial conductor to go up to the top, okay? Now, so when you, I'll run this in a minute in front of you, but what we end up when we run this, we end up with this. Of course, we resonate at 1.2275 and then 1.575. And then in this case, you can come down here to the minus 10 dB of return loss and measure the bandwidth of those two. And that's what you get in here, which is pretty good. So M3 to M4, M3 to M4. So that's 36 from 18. So that's very good. That's well around 15 some megahertz. So which is good. Okay, and this is very good. And you can see, of course, now the one of the impairments of doing this stacked business is you get the coupling between the two antennas. For instance, the L2 here, it doesn't resonate at all. It won't pick up any of the 1.57 L1 signals because the return loss is, it's basically short at that frequency. But on the contrary to that, if you look at the L1, the L1 can pick up a little bit of L2 signal, but that's really negligent because the LNA that is in that this antenna went into actually uses separate paths, so this gets filtered anyway, so we don't care. But just to see, in fact, we will show this in the performances in a minute when we go to the HFSS. Okay, the gain on these two, we're getting about 1.76 dB for the L2 and 2.27 for the L1. And like I told you, of course, these gains, this antenna is small, so this is only like 3.5 inches. So it's 70 millimeter by 70 millimeter. Most of the antennas are like that in these cases, because these are not tiny devices that go in. So that's about how much you can get. You won't get more than that. And that's why all GPS LNA front ends, they have a huge gain. They're 60 dB gain a lot of times. So the antenna in this case, because it's really not helping you a whole lot in picking up signal, okay? But it's good to have it so that at least you have selective and narrow the beam so that you can reject the interferences and the multipath. And as you know, for those of you who have been exposed to the signal processing of GPS antenna, how it extracts the phase offsets, which and the time offsets that contains the coordinate information. You would want not to have multipath. You want to try as much as possible to see a direct path to the satellite, because that's what introduces the errors, is because the whole system is based on delay estimation. So if you're getting a stronger signal from a multipath than you would be getting from a direct path, you're going to think that the satellite is actually a different location than where you are, and that introduces error. And of course, a lot of you that maybe back in the 90s when we were using GPS antennas in, like, say, cities, metropolitan cities like New York, Los Angeles, right when you go into downtown, you will notice that the navigation on the streets, you can see that it misses a lot of times. where if you go out on the open areas, it's extremely accurate. Okay, and of course, surveyors who carry these antennas, and they may have realized that most of the times is because when you're in metropolitan area, there's so much scattering and reflections, and you end up with the receiver having to cope with a lot with it. The axial ratio is something that basically what it does, it's a ratio that tells you how good is the signal in terms of, because we pick them up separately, vertical and horizontal separately. So we want to make sure that they're equal, okay? We don't mess up the ratio between them, because that actually deteriorates the signal. And so usually theoretically, what you want is 0 dB if possible, meaning they're equal, okay? And the ratio, the axial ratio is defined as this, but this is from HFSS for the dual antennas, the stacked antennas. And you can see it's pretty good. And usually these are specified. How much angle do you have between 3 dB points, okay? And in this case, of course, you can see that we have 60 degrees, that's 120 degrees, which is pretty good compared with South. The antenna itself, again, like I said, you can see the gain. We're getting 2.27 and 1.7 for both bands. And the pattern is really good. There are no shoots on the side lobes. It's pretty clean. So let's go look at these from the HFSS in a minute. One thing we could do is HFSS is good at is we can excite the antenna and see how the signal, how observe the circular polarization through the current surface density or the E field distribution in the substrates, okay? So you can actually, in this case, what I did is I plotted the E field through the feed medium, which is Teflon in this case, and then the substrate, okay? So you can see here the top substrate is being excited, and the lower one doesn't have an E field. The E field is just going through it, and that's what that is basically. That means I'm looking at the excitement of the L1 band, which is on top, the batch on top. Likewise, you can see the bottom one, and that's basically where you see here is the signal on the bottom, and you can see it. And of course, you can see how strong it is on one side and small on one side, and that's a sinusoidal distribution of E field. And that varies with time, of course, but it happens that it was picked up at this moment when same thing in here. You can see this, by the way, for the L1. Okay, so let's go to the HFSS and observe this. So let's again detail the antennas. So I'm going to do is let's hide this guy and let's hide this guy. So what we have right now is basically the lower substrate. So what we have is circular batch antenna with these slots, and then we have these here. Oh, this is the center of the. Actually, let me go hide them. So that we can at least, okay. So basically what we have right now is we have, I didn't drill a hole, but that's okay. There should be holes in here for the center pin, but in this case, because the electromagnetic simulator gives precedence to the metal over dielectric, so we didn't care. But in any case, what we have in real life, what we would have is, of course, these are the holes in the substrate for the feed to this one where we solder. In actual life, we have holes, okay, that solders to the pins. And these clearances in here are for the pins that connects to the top one, okay? So let's go and show the other batch now. let me hide the. Okay, so what I'm going to do is hide this. Okay. Okay, so this is basically the lower batch. Okay. I mean the top batch, and you can see that the if you look at side views on this, you can see that the where the these ones are the one the shorter ones, of course, is for the. I made them so that I distinguish them. This is what feeds to the top, these two here. Where the other ones are the ones that fit to the top of the lower one. Okay. Now, one thing I forgot to mention, of course, this is the lower batch has a ground plane right beneath. So let's show that again. Now, the lower batch, of course, has the ground plane. Okay, and this ground plane is very important because that's really what determines plays the ground plane for the antennas. They assume that you have an infinite ground plane, which you don't. Okay, but this is very important. And in real life, what we would have to do is this one here is actually additionally to this is also extended with being attached to another piece of plate of aluminum that will, and then we'll have a radome case. You may have seen these and for with surveyors, that so here's a globe and then that. Okay, so let's show again, just retrieve all the parts and okay, so I ran this, and of course the let's see what else. I ran this, of course, we get the this is the frequency response, the return loss, okay. Get that at 10 dB. Another one here as well. So we can check these signals, okay. So return loss is very good. As you can see, the L2 has higher Q than the L1. The gain, again, is basically this much here for both. Here, right here, sorry. Okay. The axial ratio as well here. So you can see between 68 and 74. So that's pretty good. Okay, that's almost 70. So, 70, 72. So that's 142 degrees between the 3 dB point on the axial ratio, which is pretty good. The gain again is 2.26 dB for the L1, and for the L2 is 1.78. Okay. This here basically is plotting the gain for the first one, which is 1.78. That 1.78, that's the L2. That's the L2 because the L1 is higher gain. Where this one here is for the L1, 2.27 dB. Okay, so let's look at the E field just so that we can see right now. So we've got, this is the E field right now. So let's see what frequency this is. That's 1.7575. Okay, so let's animate that and see what it looks like. So now here's the L1 signal being fed to these two elements in here to the top. As you can see, the lower batch doesn't have any E field right now, okay, in this case. And so you can see it's spinning like this, okay? And the spinning in here, of course, that's due to circular polarization. And you can play around with the actual rotation, whether it's right hand or left hand, by simply going in here and playing around with the 0 and 90 degree. Okay, so you can, in a minute, I'll show you. If you swap these, it will do the counterclockwise rotation. So this is very good sometimes to show engineering students that are doing antenna designs at the beginning. So let's stop this and let's go in and do for the other frequency. So we're gonna look at 1.227. Okay. And now we've got these two are excited. And so now you can see that the field is in the lower one. Okay. See that? Okay, so we can see that better also sideways. On this thing, you can see that the interaction is actually happening at the lower substrate. You see the E field, how it is? Okay, of course, the signal leaks a little bit into the other two ports as well. So that's basically, and okay. So let's go back to the other frequency. I didn't show it sideways. So let's go back to 1.57 gigahertz. And okay, so that would be the one on top. I can see that the shorter ones is the one feeding. I'm sorry, it's not leakage that is on the other, between the two. I'm actually exciting all four ports, okay? Of course, now you can see that it's only the, just out of curiosity. So right now we're at L1, just I'm gonna show you. So what happens is if you flip the polarity of the hybrid that feeds the antenna, the 90-degree hybrid, for instance, that would be equivalent to doing this, for instance. You can go in and put 90-degree here and then 0 degrees here, and you can watch it go the other way around, of course. Okay, there you go. The same signal, but it's going the other way around now. And of course, now this is funny, but this brought to my mind an associate of mine when I was doing an LNA design. We designed it, we did it correctly, and then we went into the anechoic chamber, attached the antenna to it, and we didn't get any signal. But I know it works because without the antenna, you feed into it a 50 ohm, it works perfect. And when we looked at it more and more, we said, what we didn't realize is the BCB layout. We made a mistake on the hybrid. We reversed the outputs of the between the 90-degree and 0-degree, and therefore now, so it was horrible because that means you have to spin the board again to correct the BCB for that. But what we did, at least for that, is you just swap basically the test equipment signals on the circle polarization. You reverse them, the vertical instead of the horizontal instead of the vertical. And at least you can get the same thing, even though it doesn't work in real life, but for the application of picking a satellite signal, extracting coordinate information. Okay, my friends. So again, I would like to thank you. And if you come to my training in February, you will enjoy doing hands-on with these designs. We're not just, we don't care about the tool, the HFSS tool. We don't teach you that. I mean, we do teach it as a sidery, but what we teach you is the design tools, the design, the theory and the design methods, and you have hands-on. We explain the theory, we detail the designs, we provide you with the open literature references and the publications, and you can go in and actually do this. We do this hands-on, step by step with a group to build these antennas. So now all you need to do, of course, on this design is actually is take this board and send it to fab. You know, you can export from HFSS to a BCB and then attach your LNA if it is on the back. We usually put the LNA circuitry right here. And so the hybrids will go in here and you can do the whole LNA on here. And then you can house it and that would be a product, just like the ones you see in real life. So you can actually, for those of you that will attend the training, you can take this and actually you will be able to send your board and actually build it yourself. And actually, we'll show you how to send it to a PCB house in China or elsewhere in the United States. And you can, they will, before you get home, the PCB will be right at your doorstep, so you can actually prove concept the actual performance of this. Okay, gentlemen, this is Dr. Mohamed Nezami. Thanking you again. Appreciate you. Thank you very much. Please keep up with my videos so you can see the next topic we're going to talk about. Thank you so much.